SERB, Government of India, he established a Pola RX-5S real-time ionosphere monitoring GNSS reference station since April 2021. He is a member of IEEE, Geoscience and Remote Sensing Society, and life member of Indian Society of Remote Sensing, Indian Society of Geomagnetics, Indian Meteorological Society, and Indian Radio Science Society. So, before wasting time, I would like to invite Dr. Sampath Kumar Panda sir for his session. Please, sir.
Thank you, Dr. Amit, for the kind introduction. So let me share this slide. Okay, is my slide visible?
Yes, sir. Slides are visible.
Okay, thank you so much, and good afternoon to everyone. Today I am going to discuss about recent advances in the GNSS applications for ionospheric monitoring and forecasting over the Indian region. So basically, before going to the ionospheric description about the Indian region, I would like to focus on the GNSS constellations. What presently we are having different GNSS constellations, and how we can use those opportunity to study the ionospheric variations over the Indian region. That will substantially help us for mitigating many things, many hazards over the Indian region. GNSS refers to Global Navigation Satellite System. Many of us know about GPS because we are having GPS in our mobile. Then all the taxi, auto rickshaw, everything, all the travel. In travel, we use GPS mostly, so for positioning and navigation solutions. But like GPS, there are few other systems are there, GNSS systems are there, which also solves the same purpose. GPS basically belongs to United States of America, and it was introduced around 1978, and it is most popular navigation system, GNSS navigation system all through the world. Similarly, we have GLONASS. GLONASS belongs to Russia, and around same time it was launched around 1982. This also available globally. Similarly, China is having its own global navigation system, that is Beidou. European Union also having its own navigation and global navigation system, that is Galileo. QZSS belongs to Japan, and it was launched around 2010. And the last one is the IRNSS, Indian Regional Navigation Satellite System, popularly known as NAVIC by India. That our Indian Prime Minister introduced the term NAVIC at the time when it was launched, and it was launched around 2013. The IRNSS architecture is quite different from those of other navigation architecture. All others are like oblique polar satellites, but IRNSS is having these geostationary and geosynchronous satellite combinations. Let us go more into the GNSS constellations. GPS is having around 31 operational satellites at present, of which 24 satellites are minimum 24 satellites are required to for the successful operation of this GPS system. GLONASS is similarly having around 25, Galileo is having 28, and Voido is having 29. Similarly, this IRNS is also having around 7, of which 3 are geostationary and 4 are geosynchronous satellites. In fact, in over Indian region, we have 2 different systems. One is the India's own regional navigation system, that is nothing but the IRNSS or NAVIC, and the second one is the Gagan GPS aided geo augmented system. So these 2 architectures are a little different. They serve for a different purpose. The first one is the IRNSS or NAVIC, that comes into picture when there was Kargil war, and our army has suffered a lot for getting the accurate location at that time, because sometimes the GPS is having some errors in that. We don't get the accurate positioning at that time. So India thought that why we cannot develop our own regional navigation system. Then they developed the IRNSS, and IRNSS or NAVIC is now fully functional. In NAVIC, we have the it is a regional navigation system surrounding, means over the Indian landmass and surrounding the Indian region will get the signals. It has 3 geostationary satellite. Geostationary is nothing but the satellites are always fixed at a location, means they will be visible at the same place always. That means they are situated on the equator of this equator of our Earth. Another 4 are geosynchronous satellites. Those are like they will revisit at the same place every day. Those will make like a 8 shape. So you can see here these red satellites are geosynchronous satellites, and these 3 are geostationary satellite. In case of Gagan, GPS aided geo augmented system, this is not fully independent system. It uses the GPS signal, and it adds the correction to the GPS signal. So any receiver on or over the Indian region, any receiver which is capable of which is compatible to this Gagan and GPS, it will receive data from both. From GPS signal, it will receive the ionospheric corrections, it will receive from the Gagan satellites, and it will calculate its own position, which is believed to be more accurate than using only GPS solutions. So in case of Gagan, we have the geostationary satellite GSAT-8, GSAT-10, and another GSAT-15, which is going to be added with this Gagan architecture. So under Gagan, we have the ground-based GPS receivers throughout the Indian region in certain grids. We have made some grids, and each grid point, each vortex point, we have the GPS receivers, dual frequency geodetic GPS receivers, which data is collected at the master station, and they will process it, and the corrections, ionospheric corrections, will be sent to the or uplink to the GSAT satellites or Gagan satellites, and those corrections in real time will be in real time with grid values will be given to the towards the users, and the user can use that, and the positioning error will be highly improved. So basically, this Gagan system is implemented for the air navigation system, and the air navigation, the aviation department in our Indian region are suggested, they have made this Gagan to make it compulsory for using over the Indian region. If you see the signals, what are the signals available for different different GNSS constellations? So we divide the signals into three types: signal 1, signal 2, and signal 3. Basically, the signal 1 and signal 2 are the legacy signals, the L1 and L2 signals, which are mostly available in most of the dual frequency GPS or GNSS receivers. The central frequency will little vary from constellation to constellation, but almost remain same within the range, so that we can any antenna which is compatible to L band, they will be receiving the data in all the constellations. So we have here mentioned the GPS, which is which satellites are in MEO orbits. GLONASS also MEO, Galileo MEO. SBAS is in geo orbits. QZSS in geo orbit. Beidou is having a combination of both MEO and geo satellites. NAVIC is having geo satellite and geoso satellites, means geostationary and geosynchronous satellites. In NAVIC, we have L5 and S bands, but most of the receivers now compatible to L5, and S bands are not available in many of the receivers because this the antenna in many of the receivers is not compatible to acquire data in such a huge bandwidth region starting from L to S band. And also NAVIC is now planning to add the legacy L1 and L1 signal. L1 signal they are going to add, so that it will be any receiver can have all the L1 signals at the same time. At a location at KL University, we have a GNSS receiver here. In fact, we have 3-4 GNSS receivers, high-grade GNSS receivers. Some are ionospheric monitoring and some are geodetic monitoring receivers. So if you see the trajectory, IPP trajectory, if you see it looks somewhat like this in a circular manner. That means the receiver looks towards the sky like a cone shape, and all the satellite paths which are available over the region at any instant of time, those data can be acquired by the receiver, and those data can be stored in the computer, and anyone can use those data for different purpose, like navigation or stationary navigation, or any dynamic calculations, or else for ionospheric or tropospheric monitoring or any timing applications. So you can see here GPS, GLONASS, Galileo, and SBAS. SBAS is nothing but our Gaussian system. Beidou, NAVIC, and QZSS. All these satellite path on a single day we have for a certain time we have plotted this, how it looks. These dots are nothing but the geostationary satellites, so they are fixed. So that's why we don't have any trajectory points for them, trajectory line for them. They are fixed points. Whereas the GPS satellites, they are GLONASS or Galileo, all those they are continuously moving. So that means the satellites are moving pole to pole, like a oblique polar path, about 2 times a day. That we can see here. In my next slide, I will show you. So there are basically 3 different segments in any GNSS or GPS system. GPS I mentioned because the usually the GPS refers to all the GNSS many times. So that's why the GNSS or GPS I mentioned here. So all are having different segments, like a space segment. Space segment is nothing but constituting the satellites. All the satellites which are around 20,200 kilometers above the Earth, they constitute the space segment. And these satellites are having clocks, and they are having transponders, and they will send the signals towards the earth 24 into 7. Means continuously they are sending the signals in a single direction, one way ranging signals. The control segment is nothing but the monitoring stations and the uploading stations. They are having, each constellation is having their own control stations throughout the globe at different places they are having, and in which they will add the time to time orbital corrections they will send, and the any corrections apply to the satellites, they will use that corrections. Second, the next one is the user segment. User segment is nothing but the users who use the GPS or GNSS signals in their equipments, like your aviation, ship, then any surveying equipments, then our taxi, and in fact the army also using the GNSS system for position. So this we have user segment in different areas, like railways, then share market, or all the in different then electrical network. Everyone is using the GPS GNSS signals for a different purpose, like timing purpose, or for navigation purpose, or for positioning purpose. If you see here an animation for this is for GPS. So the constellation is designed in such a way that every time you will get around 6 to 10 satellites. So it will help you for calculating the positioning or navigation solutions by using the signals from those satellites. Here I mentioned that around about 24 satellites are required in the constellation, but we have around 31 satellites for GPS. They are arranged in 6 orbital planes, 55-degree inclination with 55-degree inclination angles. That's why I say it as an oblique orbital path. At an altitude of 20,200 kilometers, so it is like a MEO orbit. We have the low Earth orbit, MEO orbit, then geostationary orbit. Geostationary orbit is around 36,000 kilometers. So MEO orbit is 20,000 kilometers, and your LEO orbits, low Earth orbits, these are around 200 to 600 kilometers. So the orbital time period for each satellite is 12 hours, around 12 hours, not exactly, but around 12 hours. So they move twice a day. Positioning calculation, we calculate the position in the principle of trilateration, which is different from a triangulation principle. The triangulation is used in many civilian purpose, but here their angle is calculated, but in case of a trilateration we use the range of the receiver to different satellites. Suppose I have here 4 different satellites. They are distributed in evenly over the receiver. So from 3 or 4 different satellites, the receiver can calculate its unknown position by solving the equations for 4 satellites. Satellite position is known, and through ephemeris data or orbital data we can get the satellite locations, XYZ locations, and receiver location. We can receiver location from the receiver to the satellite. We can have the geometrical range, and by calculating the time of signal travel, and by using the formalism of this the velocity of light or velocity of electromagnetic waves, we can calculate the range. So we know the range, we know the position of the satellites, then we can solve the equation to get the unknown position of the GNSS receiver. or the user. There are different grades of receivers are there, like handheld receivers are there, some good geodetic quality receivers are there, and each mobile phone is, or smartphones, all those are having GNSS receivers, either single frequency or dual frequency. Most of the single frequency users are the mobile phones or any vehicle tracking and all. Those are using single frequency receivers. But nowadays there are some mobile phones or some receivers are there which are also using dual frequency calculations for getting better positioning accuracy. So the amount or the cost of the receiver varies from a low value to high value, like some few thousands rupees to some lakhs of rupees, like 15 lakh, 20 lakh receivers is there. So the right one here, this is the receiver which is from Septentrio Polarex 5 ionospheric monitoring receiver, which is having a antenna here. This antenna is a specialized antenna, choke ring antenna. We have installed this right hand side receiver we have installed in our university from 2021. And this choke ring antenna, it is capable of mitigating the multipaths through certain algorithms, and it receives data from different GNSS constellations. Around 70 satellites are now tracked through this antenna. This is the interface of this receiver, and this one is the receiver. So this is a specialized receiver used for or customized receiver used for ionospheric monitoring. So it will in real time it will receive the signal from the GNSS satellites, and it will calculate the ionospheric indices like ionospheric electron density in terms of total electron content, and ionospheric irregularity in terms of scintillation indices in amplitude and phase. So all these data are recorded. Around 5 GB data is recorded per day. So a huge data is stored every month for ionospheric research purpose. This receiver is now joined in the joined with the global ionospheric monitoring facility at INGV Italy. What is the problem with the GNSS signals? So what are the sources of errors in the GNSS signal? There are of course different kinds of errors are there, which can be divided into around 6 categories. Orbital error, which is nothing but related to the orbital positions. Then clock error. Each satellite is having a high grade atomic clocks like rubidium or cesium clocks. Similarly, the GPS, the GNSS receivers are also having the clocks, but those are not that much high grade clocks. Those are like quartz clocks and all. And these clocks play an important role in getting the time delay for the signal to reach at the user. Similarly, third one is ionospheric delay. Ionosphere is as you know, the ionosphere is a layer in the Earth's upper atmosphere, or like we have the different layers of the atmosphere, like troposphere, stratosphere, mesosphere, ionosphere, like that. Different layers are there. So ionosphere is a medium which is a charged medium. That means it is containing the free electrons and ions which are formed during the daytime because of the solar radiation, the solar X-ray and ultraviolet rays. Those dissociate the neutral ions in the ionosphere into positive and negative ions, and because of those ions, the ionosphere behaves like a dispersive medium, and this dispersive medium allows the signal to bend inside the bend while passing through the ionosphere. So there you will expect some delays in the ionosphere when the signal traverses through it. So we have two different kinds of things in the ionosphere. One is the ionospheric delay, and the other one is the scintillations. The scintillation is nothing but the frequent fluctuations in the electron density. The first one is the large scale electron density, because of which you will get the delay errors due to the refraction mechanism, and the second one is the scattering mechanism by which you will get the scintillations. Those two are very much important in terms of the GNSS applications. The next one is tropospheric delay, similar to ionospheric delay. The tropospheric is a tropospheric layer also introduces the delays because of the neutral medium in the troposphere, like dust and water vapor and all these things are there. Similarly, multipath error also there. Multipath is related to the reflection of the signal from huge surface or water bodies or any huge buildings and all nearby the receivers. So those will also affect the performance of the receiver. Next one is the receiver noise. The hardware. This is related to the hardware of the receiver. How good your hardware your receiver hardware is. Based on that, this receiver noise also will be introduced. So our aim is to minimize all these kind of errors whatever possible to get the best solution output in case of navigation and positioning solutions. If you see the sources of error in GNSS, there are typically for GPS we have these errors like satellite clock error, orbital error, ionospheric error, tropospheric error, receiver noise error, multipath error, in which you can see around 15 meter 15 meter error is introduced in case of ionosphere. And if you use differential positioning, means if you use two different kind of receiver, one can act as a rover, the other one can act as a base station. You can minimize some of the errors, some of the common errors you can minimize, like your satellite clock error or orbital error, you can make it 0, and the tropospheric error, the receiver noise and multipath, you can multipath anyhow you cannot reduce, and but the tropospheric error you can reduce, and ionospheric error also to some extent you can reduce, because both the receivers will see the same sky, so you can reduce up to some extent the ionospheric and tropospheric errors. If you are using single frequency and single frequency receivers, it is the ionospheric error you can minimize by using some external source, like some models or some regional ionospheric maps or global ionospheric maps, or some corrections from any other services like ground wide area augmented system like our Gagan receiver, or any ground based augmented system you can use to reduce the ionospheric error in case of a single frequency receivers. Dual frequency receivers, anyhow, they use we have the two frequencies. Data can be received in two frequencies, so common error will be minimized by linear combination of frequencies in two different frequencies. So in case of dual frequency receivers, basically you will expect some very minimal errors concerning all those different kinds of error sources. If you see the vulnerability to GNSS, we can categorize them into different three types. One is due to constellation weakness. Any problem in your constellation design, that will give you the constellation related vulnerability. Then radio frequency interference. This can be either intentional or unintentional. So like people use jamming or spoofing, which are under intentional, means like enemies will put you'll use spoofing or jamming. Those are intentional things. Unintentional things also can be done in a radio operator error or non-compliant installation or equipment failure. So at present the intentional errors are as you can see in some of the news channels that the spoofing made a serious issue nowadays because of some intentional intentional interference by certain people. So this many people now interested to work on this to mitigate the spoofing and jamming. If you see the ionospheric structure, we have the ionospheric different layers in the ionosphere, the D region, E region, F region. So mostly the D region is an absorption region. There is also a less explored region. We call it as a C region, but which is not that much explored. So D region, then E layer. E layer is a conductive layer, which is in which we will have the ionospheric currents. And F region is the dispersive medium, which can be divided into F1 and F2 layers. During the daytime, based on the electron density dissociation, the some of the free electrons, they will move up, and you will get the formation of two layers, F1 and F2. However, once the solar radiation is stopped, that means after evening hours, these two will merge together to give you F layer. So during daytime, you will get the F1 and F2. So most of the electron density will be seen in the F2 layer, and this F2 layer is responsible for most of the ionospheric errors. And this F2 layer is basically corresponding to the total electron content in the ionosphere. So this total electron content we can calculate from the electron density in the medium by taking a cylindrical structure and taking a cross section. In that we can calculate the total electron content, which can be directly related to the delay error in the ionosphere, delay error introduced to the GNSS receiver in the ionosphere. So in the left side, I showed you the how the TEC calculated by taking a cross section of a cylindrical structure. The whole ionospheric effect can be seen here in two different categories. One is a total electron content, TEC, which introduces the signal delay. This is a large scale effect. The small scale effect is the TEC irregularities or plasma instability, which causes scintillations in the GNSS signals. Those are mostly corresponding to the F layer. So you can see here. So here you can see the different kinds of GNSS signals, GNSS, S-bus, and your geostationary signals, geostationary satellites. So you can see here, first one, because of this total electron content, we will get the delay, signal delay, that will cause the range error, and it will affect the user position or communication. Similarly, the ionospheric irregularity, it can cause loss of lock. Loss of lock may lead to the reduced availability because of the fading, and it may lead to signal outage sometime it may lead to outage of the signal. Similarly, the loss of lock here also can lead to the signal fading, poor geometrical dilution of precision. That means the arrangement of satellites in the sky, and undersampling of the grid-based model errors. So all these will affect the accuracy of the GNSS operations. If you consider the ionosphere, based on the ionospheric electron density, the globe is divided into different regions. Like in the left side, you can see the equatorial region, or low equatorial and low latitude region. Basically, the equator, the strip containing the equator, we can say it as equatorial region, beside which the low latitude regions are there. Then mid latitude region, then polar region. And these equatorial region and polar region, these two are the most sensitive region to the ionospheric variations, and the receiver operation over these two regions, they cause serious effects or severe effects to the GNSS operations. For concerning Indian region, you can see the equator lies just beneath the Indian landmass. That means below Trivandrum it is situated. So the most part of the Indian region falls in the equatorial and low latitude region, and that's why it is more vulnerable to the ionospheric variations, and GNSS operation over the region will be affected accordingly. Similarly, in the right side, if you see the classification here based on the ionospheric irregularity, over the equatorial region, you can see the high ionospheric irregularity in the equatorial region. Then in the mid latitude region, you will be having less, and in the polar region, moderate ionospheric scintillations you can see. So this is nothing but high scintillation, then low scintillation, and in the polar region you can see moderate scintillations. That's why these ionospheric electron density and ionospheric irregularity are two major concerns over the Indian region, because they severely affect the GNSS accuracy over the region. Although there are some of the studies have been done on ionospheric electron density error mitigation, but there are so much work to be done on mitigating ionospheric irregularity over the region. All these ionospheric variations are mostly depend on the solar effect. The sun is the ultimate source of energy. Anytime you will see there are solar energetic particles and gases. All those are traveling from the sun towards the planets, and you can see here there are different energetic particles which are coming from the sun. That too, these effects depend vary time to time depending on the activity of the sun. The solar activity changes from time to time. Every 11 year it has a cycle. Means slowly it will go to high solar activity, then slowly it will reduce and it will go to low solar activity. During high solar activity, you can expect more number of solar energetic particles towards the sun, and they will cause the solar flares, and you can see the aurora in the polar region, and in the equatorial region you will see many electric and magnetic effects that will severely affect the content of electron density, either positively or negatively. Sometimes you will see because of this solar activity there is a power outage. You can see in news channels and all, they will say that okay, there is a high storm is on progress, and you can expect the power outage or radio interference or any damage to satellites because of these effects. There are of course some incidents happened earlier, and the power outage also happened many times. So in 11-year cycle, in the right side you can see the solar activity decreases, then increases, then decreases, like that. This is approximately 11 years. Now we are in the solar cycle 25. So that means around a total 24 cycles have been completed since the calculation of solar cycle from ancient days. Basically, the driver comes from the sun, and it goes through different layers. There are different coupling mechanism happens in a magnetosphere ionosphere system. And finally, you will observe the ionospheric storms, thermospheric storms, geomagnetic disturbances, and geomagnetic induced current that ultimately affect the all the technological infrastructure on the earth. All the data are regularly these data are uploaded by different agencies like NASA. like NOAA, some many number of agencies are there. Different institutes like we have in India, in Mumbai, we have the Indian Institute of Geomagnetism in Panvel, New Panvel. Similarly, we have National Atmospheric Research Laboratory, Space Physics Laboratory in Trivandrum. All those they are participating in those in this campaign, and they are giving the data to the different agencies, and finally the satellite and ground-based data can be available here in the NASA site in different resolutions. Like starting from minute to hour resolutions, we can get the data. So anyone who wants to have study on these satellite based satellite or ground based data for space physics or ionospheric monitoring, they can use this data. Concerning GNSS receivers, yes, there are many freely available GNSS receivers are there, which are continuously monitoring the continuously recording the data over different regions. In Indian region, if you see, we have receivers in Bangalore, we have in Hyderabad, we have in Lucknow, we have in Guwahati, we have another recently one is introduced in Rajasthan. So of course there are a few. This number is few comparison to European region or any other American region, but still we can use this data for any research or any design purpose. So total around 515 GNSS stations are now active. By yesterday I checked around 515 GNSS stations are active. Apart from these, there are some regional course network stations are there. Like in case of North America, you will get a highly dense GNSS monitoring stations. Of course, in India also we have such course network, but those data are restricted at present. And there are some institutes, they are also having their own GNSS receivers, and on request they can provide the data for research purpose or any other project purpose. Under the freely available GNSS receivers, we have there are certain committees there, IGS working groups, under whom there are different they have made different groups. Like one is for a committee on the sustainable working group governance, infrastructure, ionosphere, RINEX is nothing but the how to handle the data real time, how the data can be real time available for real time applications. Reference frames, how all this data can be brought to a single reference frame so that it can be used seamlessly. Then tropospheric applications, here ionospheric applications. All those working groups are there, and they are continuously improving the infrastructure to help the community. At present, in ionospheric working group, there are 8 ionospheric association centers are there. They are developing their own regional, global ionospheric maps, TEC maps in rapid and final form. And those the center at Poland, they will collect all those real-time data from all these association centers and develop the final global ionosphere maps, which are available to the users for a different purpose. This is a sample ionospheric map over the globe. So you can see here the ionosphere is so much. The TEC is so high in the equatorial region, and it is less dense in the mid latitude and towards the high latitude regions. So like this, you will suppose this is IGS creates 2-hourly maps. So that means you can expect around 13 maps per day. So if it is 1 hour map, there are certain centers which are developing 1 hour map, or some are developing 15-minute or a 30-minute map also. So those can be used for near real time monitoring purpose. There are two different types of maps are there. One is final, one is rapid. Final ionosphere maps, there are 2 to 8 units accuracy, and the rapid maps are 2 to 9 TC units accuracy. And here I mentioned their availability, in 2 hourly availability with the grid size 5 degree to 2.5 degree longitude and latitude. So this data can be taken up by anyone, and you can do some research on this kind of data. So with this data, we have conducted some of the studies over the Indian region. Estimation of ionospheric TC. Basically, you take the GPS raw data from these stations, different stations, dual frequency GPS stations. Use the carrier phase and pseudo range measurements from those data, like this code and phase measurements. Of course, there will be satellite biases will be there, and this orbital ephemeris data will be there to help the accurate calculation of line of sight total electron content. That is nothing but the slant total electron content along the ray path from satellite to the receiver. Okay, this slant total electron content can be converted into vertical total electron content by using certain mapping models. Like one we used here, single layer ionospheric model. There are different ionospheric models also there. Like I mentioned just before, IGS global ionospheric map. These maps are regularly, those are released. Similarly, in the left side, I mentioned standard IRI 2026 model and standard plasmasphere ionosphere model. These are different data driven empirical models are there, which are available free to the public. They can use this data. However, the accuracy of this model varies from time to time. Of course, the IRI model is now updated. Now we have IRI 2020 model also. So here a study has been conducted by taking the data from GPS stations over the Indian region, comparing with different models and maps to understand how accurate representation is there in case of models and maps in terms of predictions. So those comparisons have been done during quiet and disturbed ionospheric conditions, and some statistical analysis have been done to analyze their performance. Basically, the total electron content is calculated from the ionospheric from the GNSS observables, from the code and pseudo code and phase observables. P1 and P2 are the range observables in L1 and L2 bands in case of the GPS signals, and phi 1 and phi 2 are the corresponding phase observations of L1 and L2 in GPS. So by using the frequency and phase and range relationship, we can calculate the total electron content over a specific stations by using the different satellite to receiver range paths. That means first this TC is nothing but the slant total electron content. By using as I mentioned, by using some scaling method or mapping method, we can convert this slant total electron content into vertical equivalent for simplicity purpose, and then you can use this total electron content over any region. This is a map, means a plot shown for Port Blair, Bangalore, Hyderabad and Lucknow. They are increasing order of latitude from south to north. Port Blair is towards the equatorial region, then comes the Bangalore, then comes the Hyderabad, and then comes the Lucknow towards the far latitude, low latitude station. we can see here there are discrepancies between the GPS TC and model variations like IRI, GIM, and the plasma sphere ionosphere model, and the SGP model, which is nothing but the injection of TEC with means some customized SPIM model we used here. You see here at different stations the magnitude varies. There are of course the consistent discrepancy between model and observation, and this happens because the models are global models. The maps do not have a sufficient number of stations over the region. That's why while doing interpolation operation, there is some issue in the magnitude of the TEC over the region. So that's why it is suggested to have a good number of well distributed stations so that we can have a better understanding of the ionospheric variations over the region. Similarly, these effects during a solar flare and geomagnetic storms also can be seen here by following the same principle. Here I saw the photos of this solar flare through LASCO images and the variation of X-rays from GOES satellite. So here we have considered a certain solar flare event in September 2017, which is considered to be a very extreme event. And during that period, you can see here how the solar flares are released from the sun and they move towards the earth and they cause the X-ray fluctuations and in fact they cause ionospheric geomagnetic storms and ionospheric variations over different regions including Indian region. So while studying the geomagnetic effect and ionospheric effect, there are different parameters one can consider, like the symmetric H index. This is nothing but the horizontal magnetic field component in the from the ground-based magnetometer observations that gives some indication of the ionospheric currents, ionospheric electric currents in the E region. So this is very helpful in understanding the storm progress. So you can see here when it goes down, you can assume that there is a storm in progress, the storm main phase in progress. Slowly it will go up and come to the normal position that we can say it as a recovery. The storm is slowly recovering. Similarly, the KP index also a global geomagnetic index, auroral electrojet, the VG parameters, VSW, EY is nothing but the electric field, VSW is the solar wind velocity, and VZ is the magnetic field component. So all these data can be used to substantiate the progression of the storm during any storm period or any magnetically active period. During this period, we again studied the ionospheric variations at different places, and we see how the ionosphere is the ionospheric TEC is increased or decreased over the region due to the solar flare effects. Okay, these observations are the post observations. That means the event happened and we took the data from different sources and and we tried to understand the variability. That understanding helps to implement different estimations or different prediction algorithms to know about the ionospheric variability and its corresponding effects on different technological infrastructure before the much before, so that we can have awareness or caution will be given to the users for this mitigating these effects. So there are different methods are there in which we can have some predictions, like the model, like global models are there. Similarly, some regional database models are there. And nowadays the deep learning has been introduced a lot into this field. There are the deep learning also showed substantial improvement in the model predictions. So this is the flow chart of this deep learning architecture. You can see here in the deep learning we use all these parameters which we study in the geomagnetic and interplanetary and solar observations, like sunspot number, geomagnetic field variations, then solar variation in f10.7 radio flux. Of course, the TEC, long-term TEC we used. Then DST is nothing but the disturbance storm time index. All those parameters are fed into the network, deep learning network, and we get the output of the prediction outputs. The prediction output is somewhat improved than the traditional database models like IRI and other models. Here a comparison has been done with the long short-term memory deep learning model with the GPS observed TEC as well as IRI TEC. We can see here there is good agreement between LSTM and GPS during random quiet days and storm days. So blue one is the model like IRI model, which is deviating from the GPS and deep learning model architecture. So many people are started working on deep learning application in atmospheric variability or atmospheric forecasting methods. There are we also had some statistical calculations. Our statistical calculation with means so many statistical measurements have been done by in between GPS LSTM, GPS IRI, LSTM IRI, like that different combinations have been taken to calculate the maximum absolute error, then correlation coefficients, like that different statistical measurements have been done, and we saw that the LSTM has shown improved for predicting accuracy than other models. So these are also scatter plots done between the GPS and the model outputs, and it has shown a good performance over the Indian region. This paper has been published recently in Universe Journal. Next, there is further improvement in the LSTM model. That is nothing but the by LSTM model that uses two LSTM layers in forward and backward mechanism. One can go through the LSTM architecture and you can see how the by LSTM model is different from LSTM model. There are many research articles came on LSTM and by LSTM in these 2-3 or a couple of years. So here also we conducted one study by using this by LSTM model. After successful improvement in the LSTM model, we thought of by using by LSTM model we can improve a bit more, because it uses it has the record of record at each step to have a backward propagation algorithm. So here also we considered this all the geomagnetic and solar indices along with the long-term time series of TEC, and you can see here the most more than 70% of the data sets are used for training. Then a few data sets we kept for validation, and then the rest of the days are done for forecasting of the total electron content during this period. Here we did also some statistical analysis through root mean square error and maximum absolute error during both quiet and disturbed days, and the residual points, if you see for this bi-LSTM model, this having a good distribution of like a bell-shaped distribution of these residual points. That means the within most of the data sets are remaining between -2 and 2. So this suggests that the model is working fine. We have considered this model variability by using all these individual variables solely, also by in combinations. So to see how the combinations are improved by from consideration of only single variation of this magnetic components. We did one day variability, 2 days variability, 3 days variability. Like that, we conducted a study in which obviously the 1 day variability is giving better performance than 2 days or 3 days, because the dates as they diverge from the training data. So obviously the performance of this model will be reduced. Here you can see there are two plots are given, for one for quiet days, the above one for quiet days and below one for storm days. There are like 4 different models used here. LSTM, the ARIMA model. ARIMA is nothing but autoregressive integrated moving average. Then IRI model and global ionosphere maps are used, and they are compared with this bi-LSTM model along with our observed TEC. The statistical studies here using the correlation coefficient and standard deviations, root mean square error, maximum absolute error. They show how the variations happen, and the bi-LSTM model showing here the less error as compared to other models. Here you can see the IRI model is giving the highest error in this case. And ARIMA is somewhat less, and LSTM, and then the bi-LSTM model. Of course, the GPS GIM also giving a somewhat better result than the IRI model, because this GIM contains the direct observation of GPS signals, and they calculate the total electron content from these GPS GNSS observables all through the globe by using those 500 around 400 to 500 GNSS receivers all through the world. This also is published in a good journal, IEEE Transactions on Plasma Science. Next, we try to observe the whatever I explained. Those all are about the ionospheric TEC. Those are the large scale variations, and those are corresponding to the delay error. So in many cases, this delay error is minimized by using dual frequency receivers, but we have a single many of the users are single frequency users, like as I said, the auto rickshaw, taxi, and all the mobiles and all those are single frequency users. Even handheld GPS receivers are single frequency receivers, so they need accurate estimation of ionospheric errors. So in those cases, the delay error is used, as I said, they use the ionospheric delay maps or the other ionospheric maps or models. But in case of dual frequency, as I said, also we use the we reduce the ionospheric error by linear combination of frequencies. So in most of the cases, the ionospheric delay error is minimized. In fact, the Gaggan satellite system is reducing the ionospheric delay error by taking the ionospheric grid values over the Indian region and sending the ionospheric delay error through the GSAT satellite signals towards the users. So this large scale ionospheric delay error is somehow mitigated, but the small scale effects due to ionospheric irregularity, this is yet to be studied effectively and implemented over any equatorial or low latitude region. So we also work on that direction. We have these different receivers. We have like GNSS receiver, magnetometer receivers. Here one in Tirunelveli we have, another in Alibag in Mumbai we have. So these two receivers are considered to get some information about ionospheric electron currents in terms of the magnetometer electric fields. And we have GNSS receivers. These blue and blue and green tracks are nothing but the GNSS satellite footprints, the IPP footprints over the region with a certain elevation angle. So all these receiver locations and their magnetic positions are mentioned here. Now I will go directly for this variability in terms of geomagnetic and interplanetary indices. As I mentioned in my few previous slides, similar studies also necessary here to understand the ionospheric variability, because the ionospheric and geomagnetic and interplanetary variability, they progress hand to hand. They have a coupling effect between means among themselves. So by studying one, we can get some information on the other. So that's why this study has been conducted during September 2017. That we had a solar flare during that time, and a severe geomagnetic storm happened. The storm is having main phase, two main phases actually, the two successive main phases, the stage 1 and the stage 2, and a long recovery phase after that. So we studied this event with this ionospheric irregularity structures in terms of the ROTI, rate of TEC index, how the ionospheric TEC varies from one point to other. Before that, we did a study on the equatorial electrojet. Electrojet gives information about the ionospheric electric fields over the equator that drives the ionospheric electron density to the higher latitudes. So that helps in transportation of ionospheric electron density, and also boosts the ionospheric ionospheric irregularities. Also from this the geomagnetic field variability, we can calculate the ionospheric current signatures, magnetospheric and magnetospheric and ionospheric current signatures, which in this work we can see here the d iono is calculated. D iono is nothing but it constitutes the prompt penetration electric fields and disturbance dynamo electric fields. There are two different electric fields which operate over the equatorial region when you study about the equatorial electrodynamics. So this d iono gives some information about the currents, ionospheric electric currents over the region. This we also studied, because these currents will give some indication of the reversal of electric fields during the terminators, in the terminators. That means during the post sunset hours over any region. And these pre-reversal enhancement in the ionospheric electric field can give rise to the equatorial plasma bubbles. Equatorial plasma bubbles are nothing but the irregularity structure in the electric field that rises upward from the lower part of the F region to the higher level of F region, and they move through the magnetic field lines towards the polar region, and also there is drifting of electron irregularities in the zonal direction. That means in the east-west direction as well as in the polar region. So the study in all these regions are necessary to have a good idea about the scintillation patches. So if you know the scintillation patches over your region, then the signals, the GNSS signals which are passing through those scintillation patches, those can be avoided for calculating the positioning over any region. Also, there are some models which the real-time models which used the satellite data to know about the prompt penetration electric field, that helps to know about the enhanced pre-reversal electric field over any region or suppressed electric field over any region during during quiet as well as storm conditions. So here you can see there is this red lines. Of course, there is a presence of the prompt penetration electric field that gives rise to enhanced pre-reversal enhancement, which causes the irregularity over the Indian region. To do further study over on the ionospheric irregularity, as we have a very less number of specialized ionospheric monitoring receivers over the region, we use total electron content and the rate of total electron content, an extracted data from total electron content time series to know about the ionospheric fluctuations over the region. So as I said, the slant total electron content over the region. How much time I have? Okay. Slant total electron content over any region. And from the slant total electron content, we can calculate the rate of TC and rate of TC index also can be calculated. We did a study using TEC and ROTI observations over the region, and you can see here these black marks. These are this gives rise to the ROTI enhancements over the region. Then this ROTI is classified in terms of no irregularity, weak irregularity, moderate irregularity, and strong irregularity over the region. So I'll pass a little quite fast because I have some more things to show here. The study here shows the poleward drifting of the ionospheric irregularity by taking the maximum absolute error of ROTI over the region. Also, the poleward drifting of irregularity is measured by taking certain a specific satellite signal from south to north, like one in Sri Lanka, then Bangalore, then Hyderabad, then Lucknow we took, and how it is shifted and how much delay is there in the drifting characteristic. All those are studied by using this ROTI data. This has been published in remote sensing paper. Using this available data sources, also there are studies in the depletion characteristics of the TEC depletions we calculated over the region. So I'll conclude shortly. Depletion also depletion is nothing but the TEC fluctuations happened drastically during a certain interval of time. So that also gives the information about the equatorial plasma bubble and scintillations over the region. So we have seen the negative ionospheric storm effect and positive ionospheric storm effect over the region. By taking certain specific PRNs, we can see the the presence of equatorial plasma bubbles from this the ionospheric TEC depletions. So depletions can be a proxy for obtaining the information about the plasma bubble. So these are different the plasma bubble signatures in by using the scintillation indices like S4 and phase and amplitude scintillation indices. In different constellations it is observed. So one can have multi-constellation scintillation observations. There are good opportunity in this above any region. So this has been also published in remote sensing. Traditional GNSS receiver data we take and we can use the, you can extract the S4 proxy indices. So this indices can be used also to give the information about the ionospheric variability. So this also for different years we studied. The scintillation distribution in over at any region in different directions also we see, we can see here for weak, moderate and scintillation indices. Their surface distribution also we studied, and their variation with the solar and geomagnetic activity also can be used for understanding the ionospheric irregularity variability, which can further be used for modeling of those, for forecasting ionospheric scintillations over any region. This also there is we saw the weak, moderate and intense scintillations over the region. These are the summary. In summary, I can say that there are various opportunity in on studying the GNSS and ionospheric studies over the even over the Indian region by using the lab-based GNSS receivers, the free GNSS receivers, and there are many ionospheric, many satellite-based and ground-based data available over the region. There are also satellite constellations like low Earth orbit satellite constellations. There one can use even mobile-based GNSS observations one can use. There are a few mobile models, mobile phones are there which uses the dual frequency data. We can use those also. So these are some reference papers we published. Thank you for giving me opportunity to present my views here on recent studies on ionospheric variability over the region using GNSS signals. There are of course other different instruments are there, or observatory are there, which can be used along with those. So we have a GNSS receiver here, which is continuously monitoring, and this data is can be available to anyone who is interested to work on this. Thank you so much for giving me opportunity, and thank you.
Thank you, sir. We are very thankful to you for your nice session in this international conference on behalf of our Phaltan Education Society's College of Engineering.
Thank you so much.
Heartily thank you for this your session. Thank you. Thank you very much.
Thank you.